Hi everybody, today we're going to be talking about collecting a gas over water. So why collect a gas over water? Well, if you go to collect a gas, most gases are invisible, so when you go and put it in a container, you're never really quite sure when you are done. Plus, the container that you start with probably has air, and as we saw in our last one, if we go and start collecting a gas that in a container that already has air, then you're just going to make a mixture, and that's going to make things more difficult. So one of the things that you can do is you can collect a gas, quote, over water, which is going to have its own little wrinkles and intricacies that's going on, but it is a good way to know when you are done collecting the gas, how much you have collected, and being able to measure it and so forth. So what's the deal with water? Why are we collecting it over water, and what are we going to have to take into account there? Well, remember that water evaporates, okay? So this is the only thing that you're going to have to deal with. You're going to have to remember the fact that water evaporates. Now this is our phase diagram here, and remember that evaporation is the process of being in equilibrium between a liquid and a vapor. So what we are doing is we are looking at that line right there in the liquid vapor exchange here. That is called equilibrium, and that is your vapor pressure. Now oftentimes, rather than showing the whole graph, they will simply give you a line that looks like this. But please note that this line here, no matter what of it that they show, and this line here are the same exact line. So it's like on this graph here, if they just wanted to show this, this is the graph here that you are seeing here for this guy. All right, so those two lines are the exact same line. So please note that the only thing that the vapor pressure of the water then depends upon is the temperature. No other factors matter. Now, if you want to compare different substances, we can do that at a different time, but if you're talking about an individual substance, the only thing that matters for that individual substance for its vapor pressure is the temperature that it is at. And so, consequently, if we know the temperature of the water, then we know how much of this water is evaporating, and we can measure that out in pressure units. Now, rather than look at it like a graph like this, I have supplied you with a chart that looks like this. And please note that if you look at any individual temperature here, you can get the vapor pressure. And again, I've got this chart here in torrs. Remember that a torr is the same thing as a millimeter of mercury. They are identical. And so the torrs are there for each individual temperature. So if I want to know the vapor pressure of water at 84 degrees Celsius, then that's going to be about 416.8 torrs that's there. You have access to this chart for all of the problems. No, you don't have to memorize it. That would be silly. All right, so what then are we going to do? Well, what we're going to do is we're going to collect a gas over water. So we're going to take a container that we know the volume of, and we're going to fill it with water, and we're going to invert it over a pool of water. And so that this guy here, we know the volume of that container, right? We've measured it beforehand. And then we're going to put a gas in, and that gas is going to bubble in, and as it bubbles in, it's going to push the water back out. And we know when we're done collecting, when the pressure is the same on the inside as it is on the outside, we can tell when the level of the water inside the container and outside the container is the same. And if that's the case, then because this is an open system, all we have to do is get on the internet or check a barometer, and we can check atmospheric pressure today. And whatever atmospheric pressure is going to give us the pressure of our gas. Now again, now we know the pressure and we know the volume, and we're going to be able to stick a thermometer in this, and that's going to get us the temperature. See where I'm going with this? We're going to have P, V, T. We're going to have all of these different things, and so we're going to be able to then know a bunch of information about our gas. Now there is one problem though. You'll notice that in this picture here, it says that we have wet gas. What do you mean we have wet gas? That doesn't make any sense. It's just gas. There's no water in there. Oh, Oh, but there is, because remember, what is that water doing? That water is evaporating. Even as it just sits there, it's evaporating a little bit. So we come back down here. This guy here has that orange gas in there, but don't forget that there is also water that has evaporated, because just sitting there, it evaporates. So that is considered to be wet gas because it has water vapor in with it. We have collected the water vapor along with it. Here's a good picture of it here. If I take an experiment and I start to collect that gas that is up here contains the gas in question that I am trying to collect. In this case, it's hydrogen, but there's also water molecules that have evaporated in there as well. And so not all of that gas is the gas in question, right? So what am I going to do? The whole point of this is that I was trying to avoid gas mixtures, right? Yes, but I know what this one is. I know what the vapor pressure of water is. And I also have a very simple equation that I learned in the last segment. And the very simple equation that I learned in the last segment was called Dalton's Law. And Dalton's Law says that the total is simply equal to the sum. And in this case, the total atmospheric pressure, that's what it is on the day. That's what the barometer reads, or that's what you look up on the internet and what it says. That's going to be equal to the gas in question that we care about, plus the pressure of the water, or maybe to put it another way, the VP of the water, the vapor pressure of the water. So then if I want to know what the pressure of the gas is, I just rearrange this equation, and what it comes down to is that I take the atmosphere's pressure on that particular day, and I subtract out the vapor pressure of the water depending on what the temperature of that is. So I can figure out what my gas is here if I subtract out the water molecules that I know are there that have evaporated along with it. So all I have to do is find out what the temperature is, come up here to my chart, find out what the vapor pressure is, and subtract that out from whatever my barometer is reading for that day. So here's a sample problem. It says that we're collecting a sample of gas over water, and the barometer reads 772 millimeters of mercury, and the temperature of the water is 28. What's the pressure of the collected gas? So remember, the 772 millimeters of mercury is the gas plus the water. Now, if I subtract out the millimeters of mercury of the water, then I'll be left with the millimeters of mercury of the gas. And now all I got to do is look up the fact that it's 28 degrees Celsius. So I come back up here to my chart, and here is my chart, 28 degrees Celsius. I'm going to call it about 28 millimeters of mercury there. That's a good coincidence. So I'm going to come back here, and I am going to subtract out 28 millimeters of mercury of the water. So 772 minus the 28 is 744. So whatever gas I collected there was actually 744 millimeters of mercury, not the 772. That's what my barometer read, but I have to subtract out the vapor pressure of the water. So you can see it's really easy. Number 2 here says that I collect a sample of gas over water. I've got the grams, I've got the volume, I've got the temperature, I've got the pressure. I want to know what the molar mass of the collected gas is. Oh boy, we did this already. That was back in segment 1 or 2 of manipulating the ideal gas law. So remember, PV is equal to nRT, or PV is equal to the grams per the molecular weight times RT, and then the molecular weight is equal to GRT over PV. So if I want to know what the molecular weight is, then I need to know each of these factors. Well, I do know each of these factors. Let's go ahead and plug in what I have. So the molecular weight of this gas is going to be equal to the grams. They gave me that. That was 36.1 grams. R, I'm going to go ahead and use 6236 here. So 6236 liter millimeters of mercury per mole Kelvin. And the temperature looks like it's 295 Kelvin because, again, it's 22 degrees Celsius. So I have to add 273 to that. So that's my 295 Kelvin. And then I'm going to have to divide that by the pressure and the volume. Well, the volume they gave me, that's easy. That's 5 liters, right? Now, if I were to simply go in and put in 756 millimeters of mercury here, I would be wrong. Why? Because this is the atmospheric pressure in the laboratory that day, but that is not taking into account the fact that I am collecting this over water, and if I am collecting it over water, then I'm going to need to subtractify out the water molecules that are there. So this pressure that's here is not really 756. What it's going to be is sorry about that, 756 millimeters of mercury minus whatever the vapor pressure of the water is on that day. Now it's 22 degrees Celsius here. So if it's 22 degrees Celsius, then I come back up to my chart and I find 22 degrees Celsius here. There it is, and it's about 20 millimeters of mercury for that day. So 22 millimeters of mercury, I'm going to go ahead and call it 20 millimeters of mercury, give it a little rounding action there. And so I'm going to subtract out 20 millimeters of mercury for the vapor pressure of the water. So it's not really 756, it's 756 minus 20, which is going to end up being 736. So this is going to be 736 millimeters of mercury after I subtractify out the vapor pressure of the water. So I get out my calculator and I do 36.1 times 6236 at 295 divided by 736 and the 5, and I end up with about 180. So my molar mass for this guy, or my molecular weight, is about 180 grams per mole for this guy. So this is combining those two ideas that we did before, one of manipulating the ideal gas law, and now 2, Dalton's law, and now 3, the vapor pressure, or collecting a gas over water. All of it is intertwined. One side note here, not all gases can be collected over water. Why? Well, think of a gas like ammonia. So remember, ammonia, it looks like this guy here, and it's got nitrogens and hydrogens there. And what do we know about substances that have NH bonds? Well, remember, they make hydrogen bonds. And so the ammonia with the NH that's there is going to form hydrogen bonds with the water, or in other words, it's going to be soluble in the water. So if I were to take ammonia and try to put ammonia through this kind of a system, it would not separate out from the water. It would just stay in the water because it is soluble in it. The whole point of this orange gas example here is that the gas is not soluble in the water. So it has to be an insoluble gas for this to work, because if it's like this and it makes a soluble bond, those ammonia molecules are just going to go in, and the water is going to say, hey, how you doing? I like you. And it's going to be soluble in here, and it's just going to dissolve, and you're going to have dissolved gas in the liquid there. So it will not work. You will not be able to collect a gas over water if it is a soluble substance. So in order to dissolve in water, it has to be a non-polar substance. Polar substances here cannot be collected. Polar. Anything that's polar in H bonds tends to not be very good at being collected over water because it just tends to dissolve in the water. But a non-polar molecule like nitrogen or carbon dioxide or carbon tetrachloride, these guys here, those molecules, if they try to go in the water is not going to be interested in them because they are not polar molecules. And so consequently, non-polar molecules can go in and the water will not dissolve them. And so consequently, there will be a separation of that nonpolar substance and the polar water. So only nonpolar gases can do this, because remember, water is super duper polar, and polar and nonpolar don't mix. Polar and polar mix with each other. So again, last trick is that you cannot do this method with anything that is polar, because the polar will just dissolve in the water.